report. So it's a pleasure to be here. And everything I'm reporting today, everything new is going to be joined with Dave Benson, Henning Krause, and Julia Pevtsova. And I should say that our work, at least in my mind, all the huge intellectuals get to all these people and many more. So, of course, Paul Hausdorff was all his work on PT categories, you'll see it coming all over. Then John Carlson, in particular for his work on dualisable objects in Lamont, which he talked about here a few weeks ago. Dwyer and Greenleaf, in particular for their two papers, one is complete modules and torsion modules, and one more that I've forgotten about. Next one is Greenleaf's made duality, which plays a very key role in everything I say. And especially these two volumes, the axiomatic stable homotopy theory by Harvey, Palmieri, and Strickland, and this one, which I discovered rather more recently, morphological theory and localization by Neil and Harvey, that in some sense, between these two volumes, I think they anticipate almost everything we heard today in this room. And of course, I'm not Neiman. I'm equally glad that I'm speaking last after Scott and Sanders, Marin, because all the formal constructs that I want to discuss have been introduced by them, so I can lean on their lectures and focus on telling the story. By the way, when I say this also gives me the liberty to just focus on telling the story and not worry about attributions. That's one of the reason I put it down here. Okay, so as in the last two talks, my story begins with a TP category. So T will be a triangulated category. TP category. By the way, in the few weeks I've been here, I've sort of chanced upon many discussions in the corridor on dualisable objects. So I rather suspect the audience knows a lot more about this than I do. So feel free to chime in if you think I missed something important, or sing along.
Oh yeah, I was up in my office all break, trying to find this.
Okay, one caveat. So I'm really talking about TP categories. So these will be compactly generated, but the unit object need not be compact, and this is important. So these are not. In fact, the whole story is about TP categories where the unit is not necessarily compact. Okay, and what I wanted to, I also want to, just for today, I'm going to write F for the internal function object, because I'm sure I won't be able to distinguish between the internal Hom and the categorical Hom in my writing, so this will be the internal function object.
Are you assuming that the compacts are rigid or dualisable?
No, nothing. So at the moment it's just, it's compactly generated. So in fact, most of my talk will be based on two examples, and already in those two examples you see that there will be sort of different interactions between compacts and rigids. Three examples. So this will be the internal Hom. I'm borrowing this notation from HTS. And then I'll also write D for this spanning microcontroller. So this will be F. So I'm tempted to put a SW here to remind myself that this is not Brown commonness, but it's always the dual with respect to the unit in the category. All right, and so there are three kinds of objects that I'll focus on. So I think this we don't. Okay, so X, the three properties I'll focus on are compactness. So this is just saying that forms in the category this commutes with coproducts. I don't have to say this. And then dualisable, which says that if you look at the natural map from, which is this is an isomorphism, so that's the dualisability condition. I also want to bring in one more because it sort of resonates with me in the commutative algebra and also perhaps to many of you in the audience, and that's the condition that X is reflexive with respect to Spanier-Whitehead duality. So namely, there's a natural map from X to the D applied twice, and I want to look at the condition that this is an isomorphism. Really, I ought to bring in one more, namely functionally compact, to sort of understand things better, but I'll just focus on these. And in general, these are really different notions, except that dualizable implies reflexive, and otherwise, these are really independent notions, although there are relations. For example, if one is compact in the category, then dualizable objects are compact, but in general, not necessarily. So I'll give example. I'll start with these examples soon. And I'll be talking about sort of the objects which have these properties in the category. So TC will be the compact objects in T. Compact in T. Similarly, TD will be the dualizables, and then I'll write TR for the reflexive objects. Okay. As I said, mostly my talk will focus on two examples. And the first example, context 1, is that the one, so this is going to be the derived category of a commutative ring. So A is in fact, I'll stick to Noetherian even. Okay, so we all know this is the usual tensor. So the tensor product on this is the usual derived tensor product. The unit is, of course, the object A itself, and the internal horn is the derived right? Okay, so what about the three categories I mentioned? Well, in this context, the compacts, so here one is compact. So in this context, the compacts are precisely the objects that are finitely generated by the unit object, and these are also the dualizables. So this is sometimes called perfect complexes. Things that are equivalent to bounded complexes of finitely generated projectors. Right? So in particular, this is going to be a subcategory of the bounded derived category. And equality holds precisely when A is regular. You can take this as a definition or try and prove it. Right? So what I'm trying to get at is that somehow the interactions between these categories is picking up something interesting about the ring itself. So what about, okay, so this is about the compacts, dualizables. And so I already said that the dualizables are reflexive. So the dualizables or compacts will be in, so they're certainly here. They're also reflexive. But this inclusion can be strict. And for instance, here's a fact that A is the ring A is Gorenstein if and only if everything here is reflexive with respect to the unit object. This is not entirely a trivial result. But anyway, this is true. This is one characterization of things being reflexive. Okay, of the Gorenstein property, the derived category is reflexive with respect to the unit here, which is A. So actually, all I want to use this to say is that A is Gorenstein, but not regular. What you have is that PC is strictly contained. So here's an example where there are many more reflexives than there are compacts or dualizables. Okay? Okay. Any questions?
What are the regulars? Is there a way of saying what the regular are? What the reflexive objects are?
It seems to be a bit tricky. For example, if I take a copy of A in each degree, it will be reflexive, but it won't be compact. So I don't know. I don't know if there's a nice description of all the reflexives. I'm sure in some cases, maybe in the regular case, we can do this, but not, I don't know. I didn't think very hard about it. But somehow, yeah, okay, so this is one. I want to bring in a related example here because it sort of ties in with something that Neil mentioned in his talk. So a related category. So A as before. Thank you. So A as before, let's look at the homotopy category of complexes of projective. This is projective modules. Okay. So it has a DT structure, and it's not so, in a sense, it's not terribly useful for reasons you see. So you can just tensor over it because projective is projective. You do get a tensor product. The unit of the tensor product is A itself, but already the function object is tricky. So the function object here, you take forms from so this, but this need not be projective. So that you can take sort of the. So what is this Q? So if you look at the homotopy category of projectives, this is compactly generated and it sits inside, for example, the full homotopy category, and this has a right adjoint. And you can see that this must be the function object in this category. Okay. Now, so one can also, in this context, identify the compact objects. So what about the compact? So this is actually Peter Jorgensen's result. So there is a map from the bounded Dirac category of A to K Lodge, where you send a modular or a complex to the dual of its projective resolution. So, and this is an equivalence. So this is the projective resolution of M. And it turns out that this is an equivalence. So that you can identify the compact objects in K-Proj with the bounded Dirac category of A. Okay? On the other hand, the dualizables are just the perfects. So, however, TB is just TK. So this is one computation. So I'm leaving all these exercises if you want to tune out at any time. Okay, so you can see here, this is a category where there are far fewer dualizables than compacts if the ring is not regular. So when A is not regular, we have far fewer dualizables than compacts. So it's something similar to the example. Not quite the same thing, but it has the same feature. Yes. And the other interesting thing about this example, and this is the last thing I'll say about this, is that Spanier-Whitehead duality preserves dualizable objects, but it doesn't preserve compacts, and it happens here. 1 second, Chris. So a C compact does not imply DC compact. Whereas we know that Spanier-Whitehead duality always preserves the dualizable object. Yes, Chris?
T is K, the homotopy category of projectives in this example?
Projectives, yeah. So this is another interesting feature about this category. Okay, as I said, I just brought it up to show that categories fairly close to this one have interesting features. I'm going to focus on this one. Okay, and the other category that I want to discuss is the stable module category of a finite group. John, you don't take an example? Looking askins at that example. Okay.
Is there a particular motivation to look at reflexive object, or is it just?
No, actually, for me, the motivation comes from this characterization of Gorenstein rings. Because Gorenstein, you know, what I said about this characterization, that Gorenstein rings are precisely those for which the bounded derived category consists of reflexive objects. That is more or less Grothendieck's local duality statement. Because that's really one characterization that comes from his look at. That's what local duality gives you. Because you know that the dualizing complex is an auto equivalence on the bounded derived category, and the Gorenstein property is saying precisely that the dualizing complex is really just a projective up to a shift. So that's where you get it from. The only subtlety is that's also true if you don't assume the ring has finite Kroll dimension. That's where the difficulty comes. But if you ignore that, then it's really just Grothendieck duality. So that's my reason. That's my interest in that category. Okay. So the next, as I said, the next example I want to focus on, these are only the two examples. It's a case where you have a stable module category of a finite group. So G is a finite group, and K is a field, and you're looking at a modular case. Actually, until the very end, this could also be a finite group scheme, and I can tell you at what point I have to stick to a finite group. Okay, so this has we all know the TG structure of this. It's a tensor product over K with the diagonal action. And then, of course, the unit is K itself, and the function object is homomorphisms over K, again with the diagonal action. No. The function object.
Sorry.
At least you're awake. I'm pleased. Okay, so what was that? Oh yeah, so here the interesting thing is, and here the interesting feature is that the compacts are the same as the dualizables, are the same as the reflexives. And this is the same as stamol. So in this sense, the stable derived category of a group, a stable module category of a loop, is better than the derived category of even a regular ring, because the only reflexives are the compacts. So it's like the singularity category of a regular ring. So this is it. And then, what is anything else to say about this? Yeah. So in this sense, yeah. So in this sense, the big sum. So to the stable is to the derived category of a regular. But in some sense even better, because there are no more reflexive objects than the compact ones. And this is something that will come up again, which is one reason I brought up these two examples. Okay, now I can get to second things that I really wanted to talk about: local dualizable objects. So in fact, rather than try and discuss it in some general context, let me focus on local dualizable objects in these two specific categories. I mean, the results are anyway only in this case. Let me get back to D of A. So let's fix a prime. So A, initiative about 3 years and before. And let me fix the prime P in the spectrum of A. And the relevant thing here is that it is the Balmer spectrum of the perfects, so complex, right? So at this point, I could just say, let's look at this functor Pt that Barron and also Scott constructed. But I want to give a sort of constructive definition of this because I want to make one example later on. So, given an A module M, an A module M is P torsion. I think we should be saying P power torsion. If every element of M is annihilated by some power of P, X in M, 0 for some. Yes. So it's really something, yeah. So this is tantamount to saying that M localized at Q is 0 for all Q that doesn't contain P. So this is saying that the module is supported on the closed set defined by P. That's what it's doing. So you can then look at the collection of complexes such that the homology is P torsion. This is sitting inside P of A, right? And this turns out to be a compactly generated, it's even generated by objects that are compact in dA. So this is a localizing subcategory and it has a right adjoint, which at least in commutative algebra and for geometry literature would be denoted so. So it is really the right derived functor of something called the P torsion functor. You can compute it by taking injective resolutions of objects and applying this functor gamma P, which picks up the P torsion category. So this is you get a functor like this, and so this is one functor I want to look at. So this is exactly the functor that Barron and Scott called gamma VP. And so, the other thing I want to do is look at the localization. But let me cut to the chase and define gamma P. I guess after the conversation we had this morning, I should put it like this. You look at first localize X at P, then look at the part of X that's supported on the closed set defined by P. So this is sort of the P local P torsion strata of P. Okay, and the local to global principle, which we heard about already, says that you can reconstruct X from these things. I'll skip the parentheses. So this is one reason why these functors are interesting. The other reason also was, okay, so let me say this, that let me also look at this category of P local P torsion objects. So this is the localizing subcategory consisting of P local P torsion objects in the derived category. And as we already heard, these are minimal as localizing subcategories, and somehow the key to the classification of the localizing subcategories in D of A, right? It's this. I want to focus on dualizable objects in this category because this too is a TT category. Okay? So that's what I want to talk about. And as I said, my interest, at least one reason one is interested in this category is that it comes up. These are the building blocks of the derived category in the sense that we heard before. All right. And And since it's in this category, you get a TT category where the unit object need not be rigid, need not be compact. Any questions?
You give us 2 motivations to look at this. You're short by 3. just using the time. Using your eraser.
The one motivation, I guess, is for me the main motivation is the fact that these are the minimal localizing subcategories of DFA. And the other motivation, I guess, is because of the answers. I mean, what we learn about this category as we'll see, and you already know where I'm going with this.
Yeah, it also has to do with the P completion of A, right?
Exactly, yeah. So this is sort of after the fact anyway, this is what interests me also about the category. Right. Okay. So let's focus on this category. Oops. So if I fix a P and I'm looking at the P local P torsion category of D of A, right? And as I said, this is a TT category, the tensor product. It's the same as before, the derived tensor product, only you can also, if you wish, everything is happening actually in the derived category of A localized at P. So it's the same as taking tensor over AP. But the unit will be this one. It's the P local P torsion part of A. And as you'll see soon, this need not be compact. The function object here is also just a variant, and this is again easy to check. You take the function object in the big category, but then this is also not hard to check. This is a computation you can do in any TT category. All right. Okay. So I told you already the basic structures and now we can start computing. I can tell you about the compacts. So the compact objects here, okay, so what are the compact objects here? So P of C, so this will be let me write it like this, gamma P of C, that C is in, so these are compact objects so these are things that are finitely built out of A localized at P with one proviso that the endomorphism rings of this should have finite length. Of the length of the homology of this should be finite. Okay. So these are sort of perfect complexes in A localized at P, but the homology should have finite length. Okay. Now, this one is definitely not, this homology of this is definitely not finite. And in fact, gamma PA is here if and only if P is minimal in the spectrum. It's a minimal prime in the spectrum of A. So I can already give you an example here, which might be fun to check, as I said. So, for example, if you take A to be C, the integers, and take the prime ideal to be just some prime number, the ideal generated by some prime P, then gamma PA up to suspension is, I think it's -1. So this is what it is, and it's far from having finite length. Whereas the compact objects in this category would just be the complexes of finite length and P torsion homology. Finite, yeah, P torsion and finite length. Okay, so this is the description of the compact objects here. So what about the dualizable? So this brings me to the first result, one of the only 2 results of this talk. This is one. This is maybe 2 new if. So take an object this is the p-local p-torsion category of A. Then the following conditions are equivalent. So the first one is that X is dualizable, which is what we're interested in. So that's the same as saying X is in the fixed subcategory generated by the images of the compacts, which is just saying that it's this. And just to sort of, so that it matches up with something I'll be saying about Sturmont, let me put it like this. So it's C, when C is a compact object in the big Dirac category. If you look at the images of the compacts in the big category under gamma p, then close it up. And this condition is the same as saying that the rank over X, where Kp is the residue field at P. So it's this AP. So this is a characterization of the dualizable objects in this category. Okay. So I want to make a few comments about this. So from here again, you'll see one sees that there are fewer compacts than dualizables, and with equality if and only if P is minimal. You know, if you look at this characterization of dualizable versus this condition here, we have this extra condition on finite length, which you only have for everything dualizable if P is minimal. The second point to make, and this is what Paul was alluding to, is that if you look at now, so the dualizable objects form a TT category on their own right. So the dualizable objects form a TT category on their own right, and you can look at the spectrum of this, the Balmer spectrum of this, and it turns out that this is the same as the spec of the completion of A. So localize at A and then complete it. And this, I find this quite...
Comma on the left.
Where?
Oh, sorry.
I'm always in this p-local p-torsion category. Right. So I find this to be interesting because, okay, for one thing, this map from A localized at P to its completion, so this induces a map. So and one knows that the fibers of this map can be quite complicated. So they can have arbitrary dimension. So although spec of AP and spec of the completion, they have the same Krull dimension, the fibers of this map can be quite, can be arbitrarily large. Of course, there are bounds. It can't be beyond the dimension of the ring, but more than that, it could be quite complicated. So what is interesting to me about this computation is that, so here we have this a minimal localizing subcategory, this T, which is gamma P of BA. And if you think of the spectrum of its compacts, it's just a point, right? Just a point P. Nevertheless, sitting inside this minimal one, we have an entire TT category whose spectrum is the completion. Sort of, okay.
Well,
Yeah, Paul?
the compacts don't have a spectrum, but
Yes.
the support is just a point.
Yes, the support is just a point.
And then can you remove the spectrum from 2? I mean, isn't TT equivalent to the perfect complexes of
Yes, exactly. That's how I see that. Yeah, that's going to be the other comment. That's how I see that the spectrum of that is the spectrum of the. That's how I know that it's the spec of the completion, because by Greenlee's-May, TD is equivalent to fixed subcategory generated by the completion of A. I'll write it in a second. And that's how one computes a spectrum. So once you know that the dualizables are just those in thick of, are just those in the thick subcategory generated by the gamma p of A, then Greenleaf-Smith tells you that that the dualizables are then equivalent to the perfect object, perfect complexes over the completed broken ring, and therefore you know the spectrum of the dualizables. That observation also tells you that sort of the big category associated with the dualizables is A completion, which is what you were mentioning earlier on. Okay, so as Paul was saying, the key point, the computation in of the spectrum is basically that the big subcategory of gamma PA is equivalent to really the completion sitting inside the Dirac category of the local ring completed at P. So this is Greenleaf-Smith. So this is how I know that the spectrum of this, which is the duality, is the same as the spectrum of this, which is spec of the completion. But it also tells you that sort of the big category of the so-called incompletion of these dualizables is the Dirac category of the completion. In fact, the proof of, okay, so let me say just a couple of things about the proof. Of the theorem. So 2 implies 1 is straightforward and 1 implies 3 is also straightforward. And it's sort of fairly general. You can set up, you can make those statements in some general TT context. The key point is that you have a cohomological criteria for membership in the thick of gamma PA. So the key is 3-1. And one way to do it is to pass to the Dirac category over the completion and argue there. And that's what we do, and it's a bit fiddly. But when A is regular, so there's a simpler argument when AP is regular. And let me just sketch it because this is relevant to the group case. So let's say AP is a regular ring, right? So we started with an object which is P local and P torsion. So because X is here, gamma P of dA, you can look at the homology of X. So this is P local P torsion. So you can take the minimal injective resolution. So it has the form, so minimal injective resolution. And because it is all P torsion, P local P torsion, so we know that this is some direct sum of copies of the injective hull of the residue field at P. Okay, so that's how it is. The two things, so because, so condition 3 tells you it's Artinian, so 3 implies Artinian. And that implies that in each degree, you only have to worry about finitely many copies of EP. So this is EI, by the way, not just for all I. So EI involves only finitely many copies of the injective hull. And that's what Artinian gives you. Regularity tells you that this is 0 beyond a point. That's where you need the regularity. Okay, so what it means is that you can build the homology using only finitely many copies of the injective hull. At this point, you can use an Adams resolution to say that, so that you can build the Adams resolution of X from its homology, say that X is in. So we know that this is always true, that you can build it from these things. But since this is a finite step, you'll end up with So you can use this resolution of the homology and lift it to a resolution of X. The last thing that remains for me to say is that this is nothing but gamma P of A. This is up to suspension, and this is again Grothendieck duality of the Gorenstein property. Gorenstein property of A. So that's all there is to in the regular case. One has to work a little bit harder here.
So you're proving that 3 implies 2, right?
Am I? Yes. Yes, correct. I'm proving the 3 plus 2. So is the circle not complete? It is. Good. Okay. So at least in the regular case, one can understand what's going on very easily. Okay, enough said about that. So now let me move on to the last 10 minutes or so and tell you what we know about the case in Stamod. So back to Stamod. Oops. G. And once again, I want to fix a prime in the Balmer spectrum of the compacts, which is of course the spec or the homogeneous spectrum of the cohomology ring of A. So let me call this ring R actually. This will end up playing a role. Okay, and just like in the other context, well, not in the same point in the same way, but one can construct these functors gamma P, which we already heard about from these things, and that they pick out the P local P torsion stratum of objects, and I want to look at these categories, gamma P of Stamod K. And once again, my interest in this, at least one reason to be interested in this, is that these are the minimal tensor ideal localizing subcategory of Stamod, and these are the building blocks of the stratification for Stamod, right? Okay, and once again, this is a TT category. The tensor product is as before, over K with the diagonal action. The unit object, it won't surprise you, is just gamma P of the unit. And the function object would be gamma P of the function object in Stamod itself. Right? So that's what we have. And once again, one can identify the compacts here fairly easily. And those will be the finite length objects. So let me see if I can say this. So the compact objects in this category, they'll have a similar description. So this is gamma P of C such that C is actually compact in Stamod. But it has the property that if you look at the endomorphism ring, the stable endomorphism ring, so this will be a module over R localized FP, and this should have finite length. So somehow these are the finite length objects in the P local category, the objects with finite length homology, just like in the earlier situation.
The object supported at the close point.
Yeah, exactly. And then again, the question is, what are the dualizable ones? Once again, if you already know some group homology, you know that this doesn't have finite length homology, except when P is minimal. So you see already that there are many more dualizables than compacts, but one has exactly analogous description of the dualizable objects like here. Let me write that. Maybe I should should have left it there for comparison. What is missing is this. But luckily one doesn't need that because we have system mod is like a regular ring. If the ring was regular, you could forget about KP and talk about finite length. What about the dualizables? So this is somehow maybe the main result in our work. That if you fix again, fix in T, which is KP, the following are equivalent. So X is dualizable. The same as saying that X is in the thick subcategory generated by the images of the compacts. Just like before. And then there's the cohomological criterion. It's sort of, you can, even there I could have put it in two flavors, but let me say this. So if you look at the length over the cohomology ring of this into X. So this is finite when you measure against compacts in this category. So you should think of this as being analogous to the thing I raised, condition 3, about where you had the residue field. So you can stick in any compact in this p-local p-torsion category, and I've already told you what the compacts looks like. These are things with finite length homology. So if you plug it in, you'll get something of finite length. And you can also express it in terms of compacts in the big category. Namely that this, so if you take X, this is Artinian. What I'm going to apply set P for all compact objects in the big stable category, so finite dimensional modules basically. Okay. Of course, this is, I think, somehow a better description because it's totally internal to the p-local p-torsion category. I'm only looking at compacts in the category, and it's something completely, you can compute totally inside this. This is going outside the category. It's remembering that it's coming from gamma p or something. So there is one more which...
So, are you saying, I mean, there's also a vector space dimension over K, right? And you were saying it's the same as being...
Here? Yeah, this one. Yeah. Well, but these need not be vector spaces, right? Just so finite length.
Okay, what is... okay, K is your general ring, so...
Yeah.
Okay.
But there is, okay.
K is a field. What is K is a field?
Little k is a field, but all this is happening over this localization of the cohomology ring at P. So that if anything, the relevant vector space would be sort of the residue field at that prime P.
Right, which might be different.
Which is possibly much bigger, right?
Yeah.
I get to that actually. There is a very nice description in terms of what happens at pi points. Just take a minute. I just want to, in fact, okay, I'll go out on a limb and put this here. This is on Dave. The same as saying X is reflexive. So we know dualizables are always reflexive. But in this case,
all the faces. You're looking at your code.
we have a proof, but we haven't written it down. It's been written up, but not written down. And this is a joke to something in Lurie's lecture. Okay. Okay, so once again, so this is a description, and let me just talk through this now. This already says that there are a lot more dualizables and compacts. Using this, you can, of course, describe the spectrum of the dualizables. It will be the completion of the spectrum of the completion of R, right, as before, so no surprises there. And, oh yeah, once again, the crucial problem here, so let me see if I can get the orders of implication right this time. So 2 implies 1, so sketch. So 2 implies 1 is clear. And 1 implies R. So 1 also implies 3 is clear. And 3 if and only 4 is also sum. So all these implications one can do actually fairly generally. One doesn't need the specific context of a group, some suitable TT category with maybe some local duality condition thrown in. And 4 implies 5 is also supposedly clear. So the crux is, why does, actually, 4 or 3, why does it imply 2? And this is the key assertion. This is the key. Again, what is at stake is that you have a cohomological criteria for detection of membership in this category. Okay, so notice that at this point, really it's this comes into play in the proof. The Hopf structure disappears because you can compute these cohomology groups without reference to the Hopf structure. This condition doesn't depend on the Hopf structure because the gamma p's don't depend on the Hopf structure. And that is somehow also important in the argument. So how do we prove 4 implies 2? So the sketch is that step 1 is to go from Kg to an elementary abelian group where E is some Z mod P, let me say. So this is using Quillen stratification. So you want to prove you have a cohomological condition which is not so hard to track up and down subgroups. And this condition too, thanks to Quillen stratification, you can check on elementary abelian. So the first step is to reduce with the elementary abelian case. The next step, by the way, this is where one needs that you're working with a finite group and not a group scheme. And the next step is the commutative algebras in the audience at least will recognize this passage. You go from the group algebra of an elementary abelian group to an exterior algebra viewed as a DG algebra with zero differential. So you can relate sort of the stable category of this to the stable category of lambda suitably interpreted. Okay, and the last step is to go from this exterior algebra to the symmetric algebra on, really it's the dual of this, which is just really another way of saying you have a polynomial ring in A variables where each of them has degree -2. Homological degree -2, so it's on the cohomological side of things. And it turns out that here there is an equivalence of categories between K inch and the derived category of S. This is the BGG correspondence. We know the answer here from what I said. So this is also a regular ring, so we know how the dualizable objects in p-local p-torsion categories. So from there you immediately get it for this category, and these two categories are fairly close. One understands that passage, and then you ascend to Kg using Quillen stratification. So that's sort of the structure of the proof. And this is really where the specifics of the groups come in. Okay, I should stop here.
Thank you.